Hi everyone, in this video we're going to see the basics of Bayesian inference. So far in general what we do in machine learning is to first identify the task, then after we decide what is the task we will use to approach a given problem, we find the best model for it. And finally, whenever we get new unseen data, we just use the same model we found. For example, the task could be a classification problem, a regression, or a clustering problem. And when we find the model, in the classification case is going to be, for example, a decision tree. If in the regression case or prediction could be finding the regression weights. And in the clustering could be, getting the best centroids by using the k-means algorithm. And then whenever we get to use our models, usually, for example, in the classification case, if we get a new data point, we must travel that data point through our tree to see what is the predicted class. Or if we get a new data point in the regression case, we will have to multiply that point by the weights to predict the output. Or in the case of clustering, if we get a new data point, we just need to find what is the closest centroid to that new data point to decide to which group or cluster the new data point belongs to, right? For example, we need to identify the task here. So we can say, okay, we have data points and the domain is T, and we need to predict the value of Y for the unseen data point. So we will approach this as a regression problem. Okay, so now we find the model. Let's say the green line is the model we found. And then whenever we need to predict for a new data point, we just need to multiply our new data point by the parameters theta. If we have a new data point located at t equals minus 0.7 and we need to find y, we just project and use our model to know the prediction for t. But here we have a problem. By using different parameters or different initial assumptions, we get different models. And all these models kind of make sense, right? It's hard to tell which one should be the right model. And that situation becomes even worse when we have areas with no so much training data, like in here, right? You can see that now we have in the middle a big gap where we don't have training points. In this case, when we go and train our regression model, we get this situation. Very different approaches or resulting models in the areas where we don't have training data. So imagine if we don't take care of this and we just grab any model and we deploy it and tell to our client, I have a brand new model and it's already deployed, ready for you to use it. That would be a big problem, right? Because our client would never know this situation in where we had very different predictions among our models in the area where we didn't have training data. What we really want is something like this, in where instead of just one model, we have a model that is passing us all the uncertainty, and we understand that there are areas in where uncertainty is bigger and we shouldn't directly believe to what the model is saying. So in this figure, we can see that one thing is the yellow line that in the first case was just one model, but now the green areas are showing us how much uncertainty we have in that given area. So in zones where the green areas are bigger or wider means that the uncertainty is bigger and there are many possible models that could fit in there. From a math perspective, this means that instead of having just one W or theta as a set of parameters, we're going to have a distribution of parameters. So why dealing with model uncertainties is a good thing? In some cases, we have safety issues. Imagine that we have a model that needs to predict if there is a stop signal at the corner or not for a self-driving car, right? If we blindly believe what the model is saying, we wouldn't care if the model is telling us, there's no stop signal with uncertainty 0.9 versus uncertainty 0.1, right? Of course, if the model is telling us, I believe that there's no stop signal, but I'm very uncertain here, we would better decide not to hear the model and maybe make the stop anyway or ask a second model. Another very important application and use in practice is that when we deal with uncertainty, we know much better where to gather new training points. For example, here, we know that if I have the opportunity to go and ask for new training data, I would prefer to have training data in areas where my current model uncertainty is bigger. That is very useful, especially when training data is expensive. Pay attention that what we're talking about here, it doesn't mean that we just need class prediction probabilities. In the case of the random forest model, which is a set of decision trees, we know that we can obtain probabilities on the prediction by just counting the number of trees that are voting for a given class divided by the total number of trees. That's an estimation of the class probability, but it doesn't mean we are dealing with uncertainty. Same here. In a traditional neural network, in general, we can have probabilities for each of the classes when the network is predicting. But the problem is that that uncertainty is not capturing the uncertainty coming from the model itself, right? It is just one neural network with one fixed set of weights or parameters. There's no model uncertainty. The version of neural networks that deal with uncertainty are called Bayesian neural networks, and in those cases we manage distributions of the weights instead of just one weight. And in that case we are really dealing with the model uncertainty. So what really means to be a Bayesian? Instead of finding one model, we find a distribution of models. So instead of having one prediction that relies on that model, we get a predictive distribution that relies on all the possible models we have in the distribution. In many cases, you know that our models are just a set of parameters. Let's say theta, and theta has p parameters from theta 1 to theta p. When we train a model, we basically find the best set of parameters for our purposes, and we call it like theta hat. So the key here is that instead of finding theta hat, or the optimal set of values, we find a distribution for theta. Okay, so summarizing again, instead of one model, we have a distribution of models, and instead of one theta, we have a distribution for theta. From a prediction perspective, instead of having one prediction that relies on one model in particular, we're going to have a predictive distribution that relies on all the models inside the distribution. And instead of predicting by just going and multiplying the parameters times the new data point, we're going to have a probability of the output given our data point. So it's a much richer representation for our prediction. So let's dive in, right? So what it means to have the probability of the prediction given the input and the prior data. Well, coming back to the regression model, right? Here you can see that the prediction is a distribution because it's taking into account the level of uncertainty in the area where I'm asking to predict. We could have, for example, one-dimensional normal distribution there, or any other distribution, more complex distribution, right? So let's break down the notation. Let's say we have our historical data that are data points from 1 up to t, and then we get a new data point at xt plus 1. So then we need to find yt plus 1, right? So this is going to be the prediction for the output. This is the previous data, the one that we used to train the model. And this is the new location where I want to make the prediction, right? So we can summarize that writing all the list of historical data. We just can call it data. Okay, so let's find how this distribution looks like. In general, we're gonna need to add the parameters because we know that we cannot make a prediction without knowing the parameters. So what we do here is like we add the parameters we need, but since we don't know it, we need to multiply by its probability and integrate across all the possible values of the parameters, right? This is just the law of total probabilities. And every time there is a variable that we need to include but we don't know its value, we add the variable and then we sum or integrate across all the possible values of the variable. If our set of parameters are continuous, then we're going to have to make an integration. If it's a discrete parameter, we will just do the summation. Now, taking advantage of some of the independency relationship, here, if we already know the parameter, the parameter is right here, then our prediction doesn't really need to see the historical data because somehow that information is summarized in the value of this parameter. And at the same time here, the probability of the parameter only depends on our training data because it's the only thing we're going to use to get that parameter. We cannot use the new location because there's no value for the prediction here. So we can delete that from our term. So now we can rewrite that and let's go over each of these terms. Here, we call this term the posterior predictive in the Bayesian world. Means that this is the distribution of our prediction. And here we have two very important terms. The first term is just one regular prediction because we have one of the parameters set here. So we can just go and predict by using our model. But this term, the model posterior, is very important. because it's going to work as the weight we are applying to the prediction here. So imagine we are going over each possible value of the set of parameters theta. Then per each of these value, we are going to make a prediction, but the prediction is going to be multiplied by this posterior. So when our set of parameters is not very likely, or we have a low probability here, the prediction is not going to be taken into account so much. But whenever we predict with a theta parameter that has high probability, then that prediction is going to weight much more in our posterior predictive. This is key to understand. Our final distribution or posterior predictive is going to go over the prediction using all the possible models, and on each of the predictions is going to be a weight telling us when to believe more or when to believe less to the model. And that is going to be governed by the model posterior.